All right.
Thank you. It's not free breakfast if you keep you just pay for it later. It's almost like you just pay for it later. It's free now until you pay for it.
So, all right. Graph f prime given to us here. Okay, so the figure above shows the graph f prime, the derivative of a function f. The domain of f is the set of all real numbers x such that -3 is less than x is less than 5. All right, so that's our interval. All right, for letter A here, we're asked for what values of x, does f have a critical value from -3 to 5? So let's just answer that question first. So volunteers here, where do we have critical values for f? Sean? Okay, so critical values at x equals -2, x equals 1, x equals 4. One moment. Hello? Hey. Everything should be on the classroom for him. Okay? Bye. Okay. So critical values are there. Okay, and Sean, how did you determine that those were the critical values of f? Where the slope was 0? Where f prime had zeros, right? Where f prime is equal to 0 or does not exist. Of course, f prime here exists for the whole interval there, but we do have some zeros of f prime indicating those critical numbers or critical points. Yes?
What would it look like on a graph if f prime didn't exist?
So it would be like a discontinuity. It would be like a discontinuity there, like a whole asymptote, something like that. Okay. All right. Good question. Determine then whether each is a relative maximum, relative minimum, or neither. Justify your answer. So let's just go through these in order here. All right. Anybody? -2. Is that a relative maximum, relative minimum, or neither? Relative maximum. So x equals -2 is a relative maximum because f prime changes from what to what here? Positive to negative. Oy, oy, oy. At this point. Okay. All right, let's see here. What about at x equals 1? Relative maximum, relative minimum, or neither? Neither, okay, neither. And so is neither because, and we can say here, like, because f prime does not change from positive to negative or vice versa at this point. Or you can say because f prime stays negative on both sides or something like that, okay? Is neither because f prime does not change. You can change, does not change signs, does not change from positive to negative, negative to positive, any of those things. Negative or vice versa at this point. Okay. And then lastly here, what about at 4? What do we have there? We have a relative minimum because f prime changes from negative to positive at that point. At this point. Okay. Please be careful about, yes, Simeon?
Would endpoints not classify as critical points?
Correct. We don't want to, well, in the case of, especially here, we wouldn't count -3 or 5 as a critical point because they aren't where the derivative equals 0 or does not exist. So the critical points, by definition, 0 and does not exist. When we evaluate absolute extrema, remember that we kind of differentiate between the two. We say we have to check our critical points and our endpoints when we're doing the absolute stuff. Okay? few things I do want to highlight here. Please make sure you don't use pronouns, okay, unless you've already established that you were talking about f prime in the first place, okay? So please make sure that you're not saying because it changes. Make sure you're saying because f prime changes, okay? Be specific so that way you don't leave any, guesswork to the grader about, what it refers to. All right. Also, let's see, what else did I want to say? Oh, again, please no abbreviations in your descriptions too. Again, if you do it here in the notes, that's okay, I guess. But again, I'm always an advocate of practicing like you're going to play. And so if you abbreviate here, you're more likely to abbreviate on the test or something like that in a moment of, just not thinking. So please don't do that. Yeah, Matthias. I don't know. And that's why I say just go ahead and spell the word out, okay? I don't know. Definitely a big no-no. Definitely a big no-no is to put a minus sign for the word negative and like a plus sign for the word positive. So don't put a minus and a plus, okay? Definitely I can say I will take points off if you put a minus sign and a plus sign. Minus means subtract, plus means add, okay? Yes, in our little number line thing, that's fine. We can use the minus and plus sign because that's in a number line. That's not part of our justification. But in your justification, you need to use words. Okay? You can use mathematical symbols here in this case, but minus and plus don't mean negative and positive. They mean minus and plus in that case. Okay? So please make sure you use the words. I know for a fact that can cost points. Okay? So, next thing, letter B. On what intervals is the graph of f concave upward? So, for f concave upward, if we're given the graph of f prime, we want to know when f prime is what? Increasing. Because where f prime is increasing, its derivative f prime prime will be positive, and therefore f will be concave up. So we are increasing here from -1 to 1. Okay, -1 to 1, union 3 to 5. Because, as I just said, f prime is increasing on these intervals. Okay. All right. Letter C, given f of 1 equals pi and g of x equals -2e to the f of x, write the equation of the tangent line to g. Tangent line to g at x equals 1. Okay. How do we find the equation of a tangent line? What do? We need two things? A point and a slope. Do we have a point? Already. We kind of like have half of the point, right? We know the x coordinate. We need to find the y coordinate here. So we'll do g of 1, which is equal to -2e to the f of 1. What is f of 1? Pi. So we know -2e to the pi. Okay, g of 1 equals -2e to the pi. And so that is our result for that's our point then, 1. Okay. And then how do we find the slope of our tangent line? Take the derivative of g there. So g prime of x equals, so that -2 is just a coefficient. We can leave it alone. The derivative of e to the something, e to that something times the derivative of that something. Okay? And then we can multiply by the derivative of what's inside that, but the derivative of x is just 1. So we say times 1 if you want to, but we don't need it there. Okay, we'll say g prime of 1 then, which is -2e to the f of 1 times f prime of 1. What is f prime of 1 though? Yeah, there's the derivative, there's graph f prime at 1. It's 0 is its value there. So this thing is 0, so times 0, the whole thing is just 0. And so we have y plus 2e to the pi, minus a -e to the 2 pi. Right, equals 0 times x minus 1, which in other words is just y equals -2e to the pi. Okay, so that's a horizontal line that goes through the number -2e to the pi there. Okay, you could also circle this too. This is fine as well. Right, that's also okay. Okay, given g as defined above, for what values of x does g have a relative maximum? Justify your answer, okay? So how do we normally find the relative maximum of a function? What do we do? Not prime, nope, not necessary at least. We can take the first derivative, right? So just use g prime of x, which we know is -2e to f of x. Now, Mario, you're not wrong. We could use the second derivative test, but we first need to get those critical points, okay? So we could use second derivative test, but we need the critical points in the first place. So, let's see here. We want to know, first of all, our critical points here. So when does this thing equal 0? Or when it doesn't exist? Right? You got to find those critical points for our function. Or our derivative, I guess, g. Okay. This is weird. We don't know what f is, but we're supposed to figure out when this derivative here is equal to 0. When does this equal 0? Not never. At -2, 1, and 4. Because, so let's examine our pieces here. When will this first piece ever equal 0? Never, right? It's impossible because we're taking e, which is like 2.7, to a power. So it's going to be 2.7 to a power times -2. That's never 0. So it's never going to be 0. But we're multiplying by f prime of x. When is f prime of x 0? We found those back in a, didn't we? It was at -2, 1, and 4. And so we have that interval there, -2, 1, and 4. And so we have to pick numbers. We have to pick numbers inside those intervals here. And I guess I should really, have -3 and 5 as my endpoints there, since f doesn't exist beyond -3 and 5. Okay. So let's pick a number between -3 and -2. Let's say -2.5. Okay. What is f prime at -2.5? Positive or negative? Positive. Right? Because if you look up here, -2.5, f prime is positive. Okay? F of -2.5, who knows what that is, but e2 f of -2.5 is going to be positive times a -2, negative. So negative times a positive, this interval between -3 and -2 is negative. Okay? Let's pick a number in here. Let's pick 0. That's a nice one. Okay? F prime of 0, is that positive or negative? Negative. E to the f of 0 is still going to be positive. Times a negative is still be a negative, so it's a negative times a negative, positive. Okay? This first piece here, it's always going to be negative, right? E to something is going to be positive, but then times it negative. So we're always going to have our first thing be negative there in those intervals. It's a matter of what f prime is. All right? Between 1 and 4, let's pick like 3. F prime is negative, so negative times a negative, still positive there. And then between 4 and 5, f prime is positive, so negative times a positive, negative there. Okay? So, does G have a relative maximum? Where? At 4. At 4. So we could then say at x equals 4, G has a relative maximum. Okay, because, why? G prime changes from positive to negative at that point. Okay. So there it is. You might also be able to justify this. You might also be able to justify this from the second derivative test. I mean, you'd have to take the second derivative of G prime and then plug the critical points, -2, 1, and 4, into the second derivative. See if you could evaluate it from that way. Might work, might not. I don't know. So, but the first derivative test also works there. Okay? Questions on any of that? Okay. I wanted to actually go back to, let's see here, which one here? Okay. If we look at example 5 here, okay, remember answering these questions? I didn't end up justifying it there because, well, I didn't want to. I'll show you here the justification for it from the official, like, AP scoring guideline here, okay? So this is from, like, a practice test, I think the 2000 practice test. It's the AB, I think, practice test. But either way here, you can see this is the normal, like, scoring rubric for a free response question, okay? So you can see here for letter A, and this is kind of like how we try and grade your free response questions as well, okay, based off of, like, how we think the rubric would look like, you know, for particular questions on, like, your tests and stuff. We can see here, right, the different answers are provided here, and then also your points, okay, and how they're given, all right? So, for example, letter A, you had 1 point for the answer and then 1 point for the justification. It's kind of like, duh, right? You're asked to find the place and then justify why it's so you get 1 point each there. Same thing for B, the answer and the justification each get you a point, okay? And then letter C, we get 1 point for the first interval, and then you get a second point for the other 2 intervals, which is kind of interesting there, okay? Why they decide to do that, I'm not really sure, okay? But that's just the way the points worked out there. And then for letter D, you can kind of see, again, we skip this analysis. All right. But notice where you get points. You get 1 point for identifying the correct location, 1 point for identifying the candidates, okay? Or you get a point for indicating the graph of f increases, decreases, then increases. Okay, interesting there. I guess that's because that's like kind of like identifying those. And then you get 1 point for justification. So let's say that you just like completely screw up the justification. That's only 1 point out of the 3 possible that you miss out on, which is not that not that significant when it comes down to it, right? This massive justification, which can be kind of complicated, and we're not quite ready for because it talks about some stuff in there that we haven't quite covered. You can still get 2 out of the 3 points there, even if you do mess up the justification. Okay. So again, try and answer as much as you can, get as many points as you can for those. Likewise here, I wanted to look at the one prior to that, example 4. Okay, you can also just kind of see the scoring guideline here. Okay, again, 1 point for identifying the correct locations, 1 point for your reason or justification. Letter B, again, indicating that f decreases then increases, part of your justification, eliminating x equals 5 for being a maximum, and then identifying the absolute minimum and absolute maximum there too. Okay. So again, even if you can't get the justification, you can still get points for identifying the correct absolute extremum. All right, and then letter C, 2 points for doing the derivative correctly. 2 points, and then only 1 point for the actual tangent line equation itself. Okay, even though our ultimate goal is to find the equation of the tangent line there for part C, you get more points just for correctly taking the derivative of g prime. Okay, so again, the purpose of this is to kind of just let you become more familiar with how things will be scored for these free response questions. Half of your test is going to be free response questions. Half of the points in your test for the AP test will be free response questions. The other half will be multiple choice. This is where students tend to pick up the more points, actually, is the free response questions, believe it or not, because you have these partial credit availabilities and stuff like that. Okay? All right. Let's move into optimization. All right. Good times. Okay. We've been away from word problems for too long here, so we're going to jump into some. Okay. So, one of the most common applications of calculus involves determining maximum and minimum values. Duh, right? It's really helpful. Hopefully you guys can understand that, right? To find when something attains its highest, level of something, and when something attains its lowest level of something as well. All right. The process of finding the maximum minimum of in a context is optimization, right? Trying to find the best or the least, or highest or the greatest or least, kind of value. Okay, so here we're going to jump right into the strategies for this. Okay, these may at first glance look like related rate problems, right? Because you're like, oh look, there's a shape, and we would take the derivative with respect to time and stuff like that. Not in this case, okay? But again, the setup is similar though. So first, we're going to assign symbols or variables to all given quantities and quantities to be determined. Okay, when feasible, make a sketch. We've already got a sketch here, so that's nice. 2, we're going to write a primary equation for the quantity that is to be maximized. Okay, so we're going to, within the context, we'll be given something that we're trying to maximize or minimize. That's our primary equation. At times, because that primary equation may have more than one variable, we want to reduce the primary equation, rewrite it so that it only has a single independent variable. Okay, so for example here, you can see the surface area formula. This actually is this is not what we're trying to minimize, but if you look at the surface area formula, right, it's got x and h in it, so we would want to maybe, if we were trying to maximize or minimize surface area, we'd want to rewrite this only in terms of x or only in terms of h. So how do we do that? Well, it may involve the use of a secondary equation that relates those independent variables of the primary equation. Okay? Then finally, we'll do the calculus part and differentiate the equation and solve for the critical values, because again, how do we find extrema, right? We use the critical values. And then we'll determine the desired maximum or minimum value depending on the situation. Okay? So, example 1. A manufacturer wants to design an open box. Open box means the top is opened, right? Having a square base and a surface area of 108 square inches. Okay? So we're told the surface area of that box is going to be 108 square inches. What dimensions will produce a box with maximum volume? So our constraint is that we want the box to have a surface area of 108 square inches. Not really sure why that might be the case here, but that's what we've got. Okay? We want to then produce, with this restriction, we want to produce a box with maximum volume. So we want to maximize the amount of stuff that box could contain, given this constraint that we have 108 square inches of surface area to work with. Okay? So, what is the thing that we are trying to maximize or minimize here? Is that what the question says? We're trying to maximize volume, okay? Volume. Now, what is the volume formula here? Well, let's take a look. We have an open box that has a square base. So the base, if I say this is x long, then that means this side will also be what? X is a square base, right? Now, we are not told that it's a cube. If we were told it's a cube, the problem would be over and done with because, well, we would know that the height would be x as well. We don't know that it's a cube, so we're going to have to call the height h, a separate variable there. Okay? Unknown. Okay? And so then what would the volume formula for this particular box be? X squared h. Okay, length times width times height, so x squared h. Exactly right. Okay? Now, looking at our primary equation, we can see in step 3 here, we're supposed to reduce the primary equation to one having a single independent variable. So if you look here, do we have a single independent variable here? No, we have two, right? We have x and we have h. Those are both independent variables. And then v, that's our dependent variable because it's like, that depends on what the values of x and h are there. Okay. So we need to rewrite this equation. How can we do that? Well, this may involve the use of a secondary equation. What other relationship do we have? What other piece of information are we given about this box? Surface area is 108 square inches. There's our surface area formula. Okay, now let's just kind of examine this, make sure it's legit, okay, right? So you can imagine this box is open-topped. So if we're talking about the surface area, that means the bottom of the box will be, will exist, and that's going to be a x squared area, right, x squared. And then to that, we're going to add 4 xh's because each of these kind of like lateral or side faces will be an area of xh. There's going to be 4 of them. And of course, the top is open, so there won't be an x squared on top. So just 1 x squared on the bottom and then 4 xh's around the side there. That's our surface area. But that's going to be equal to 108. So this is our primary. This is our secondary. Okay. The secondary is used to be able to then rewrite the primary in terms of a single variable. Okay, that's all it's for. So we'll say 108 equals x squared plus 4xh. Okay, now, looking at our secondary equation here, we have both x's and h in there, but which variable should we probably solve for, given the way it's written? Probably h, right? There's only a single h here. Solving for x could be tricky and maybe impossible because we have those x squared and x's there. But the h by itself we can get. So, okay, there's that. And then we'll get the h by itself by dividing everything by 4x. So we have 108 minus x squared all over 4x. Okay. So now, again, we've used our secondary equation there for its purpose. Its purpose is to be able to then get the primary equation in terms of a single variable. So this h here is the same as this h right here. So we're going to do a substitution. Okay, like that. Okay, substitute in for h there. now we have v in terms of a single variable x. This is helpful because now if we were to go take the derivative of this, it would be a lot easier, right? We wouldn't have to worry about like implicit differentiation or anything like that. We would have just v over here, we'd have x's over here, and we can then take the derivative and maximize it. Before we take the derivative, though, what should we probably try and do with this? Yeah, multiply, simplify it out some, right? So I'll go ahead and do this. There's like a couple of ways you can think about doing this here. Maybe I'll cancel, well, no, I'll distribute the x squared through the numerator first. So I'll make it 108x squared minus x to the fourth all over 4x. Okay, I'll also go ahead and do the division here as well. I'll do the division, all right? I know this is going to be like, we're treading on a little bit of like, you know, unsteady ground there because when I do that, I'm going to be eliminating that denominator there where x could be 0, this could be undefined here. But of course, if x is 0, we wouldn't even have a box. So it's not really necessary to consider the situation when x is 0 there because we're trying to make this box. I'm assuming that, you know, we don't want our box to not exist. So if x was 0, the box wouldn't exist. So we're not going to worry about that situation. We'll just go ahead and do the division here. Okay, so 108 divided by 4 is 27. And then x squared divided by x is x. And then we'll have 1/4 x to the third there. Okay, don't forget that 4x divides both the 108x squared, but also the x to the fourth as well. So x to the fourth over x is x cubed, and then 1 over 4 is 1/4 there. Okay, so that's v. Okay, so just any questions up to that point? Any questions up to that point? We're all good so far? All right, so now we finally have v in terms of a single variable, and we still got to maximize this thing. How do we find the maximum of a quantity? Take the derivative, and then what? Find those critical values. So minus 3/4 x squared there. Okay. And so we'll set it equal to 0. Okay, we'll add the 3/4 x squared over. Okay, multiply both sides by 4/3. I guess I'll show that here. Okay, so 27 divided by 3 is 9, times 4 is 36. And then square root both sides here. X equals plus or minus 6. Okay, so there are our critical points. Bless you. Can we do anything about that plus or minus 6 though? Can we throw out one of those? Right, -6. In the context of the problem, since we're in a context, it doesn't make sense for x to be 0, and it certainly doesn't make sense for x to be a -6, right? How would you make a box with a -6 side length, okay? So we're only going to worry about 6 then, okay? Certainly 0 is like a lower kind of, again, I'm going to put 0 on my number line there for our analysis of whether we have a relative maximum or minimum there. I mean, granted, we've got one critical point, right? So it's like, that's probably got to be the place, right, where we're maximizing things. If we don't have that, then where else would it be, right? But we'll push forward with this and stuff and just make sure that it is a maximum. All right, so we're going to pick a number here between 0 and 6. Let's say, I don't know, 1. We'll plug 1 in. Where do we check that 1? Into the original? Into the derivative. We want to see what the sign of the derivative is. Plug it in here for v prime. 1 squared is 1, so 27 minus 3/4, positive on that interval. And then after 6, I don't know, let's pick like 10, just make it easy. So 10 squared is 100. 3/4 of 100 is 75. 27 minus 75, negative. Okay, negative. So, are we convinced then that 6 not only is a relative maximum, but it's also going to be the absolute maximum here? Are we okay with that? Okay, prior to 6, right, starting at 0, which is the lowest we could possibly have our x value there, starting at 0, we are increasing, f is increasing all the way up to 6. Sorry, v is increasing all the way up to 6. And then once we hit 6, v starts to decrease. The volume is going to start to decrease forever in that interval there. Okay? And so where's our maximum? Okay, the maximum is at 6. Okay? So and absolute maximum. Okay. Of V. Okay. So the question, though, have we answered the question? We've got one dimension. We've got the 6. So x is 6. But how can we find, what other dimension do we still have to find? H. How can we solve for h here? What can we do? Plug 6 back into where? That secondary equation right there, right? So we got 108 equals 6 squared plus 4 times 6 times h. Okay, so that's going to be 36, but taken away from the 108 is going to leave us with 72. 24h, divide both sides by 24. H is 3. Okay, so our final dimensions then are 6 inches by 6 inches by 3 inches. Okay, h is 3 inches, x is 6 inches. Okay, so there are our final dimensions that would maximize the volume of that box. Yes?
Did you just plug in to, like, you know how we did the secondary equation when we got h equals?
Mm-hmm. Oh, yeah, gosh, that's true too. I could have just plugged it in there where we already had it solved for h. Probably a better idea, Sean. Yeah. Ready, a better idea. Okay? Good catch. Other questions on that one? All right. Let's continue here. So, situation number 2, a rectangular field bounded on one side by a building is to be fenced in on the other 3 sides. Okay? So we're going to have a building that's big enough to bound or to provide one side, and then let's just say, I don't know, here's our field. Okay? Rectangular field. Okay? So, it's bounded on one side by a building, and it is to be fenced in on the other 3 sides. So is there fencing on all 4 sides of this field? No. Okay, the building is acting as one of the sides, so we don't need fencing there. All right? So our dimensions, you can kind of make them up how you want here. I'll call this, maybe this width here, I'll call that x, since that's like a horizontal distance, and I'll say these are both going to be y, or something like that. Okay? We don't know those. Notice again, I am not labeling the building there because that doesn't have any fence. There's fencing here, here, and here. Okay, these are both going to be y because opposite sides in a rectangle are congruent or equal, right? So that for sure is our label. Okay. Okay. If 3,000 feet of fence is to be used, find the dimensions of the largest field that can be fenced in. Okay. So what is our primary equation here? We're trying to maximize the what? I hear perimeter, I hear area. Both of these things are showing up in the problem, but what is the thing that we are trying to maximize? We're trying to find the largest field that can be fenced in. That would result in using area there. So, what is the area formula for this particular shape that we're trying to maximize? It is x times y, length times width. Length times width there. Okay, length times width. Okay, that's the area formula. But what's the problem with our area formula here? 2 variables, right? We only want to have it in terms of 1 variable. So we need a secondary equation. Again, there's our primary equation, what we're trying to maximize or minimize. Let's go to our secondary equation. Okay. And our secondary equation will be the what of this field? Perimeter. Okay? We know the perimeter has to be how much? What's our perimeter limit that we've got? 3,000 feet of fence, okay? 3,000 feet. Right, why don't we just make a circle with it? Well, I guess you could. I guess you could. That might make our calculations a little bit more difficult. I'm not sure, but rectangle is what we're going to go with here. All right? So, what would the expression for the perimeter of this field be?
2y.
Oh, x plus y squared?
2y plus x.
X plus 2y.
Yeah, if you were to just take the derivative of that.
Yeah, this is right. It's so easy. Yes.
I think I just have to take the derivative of it.
Okay. All right. So now looking at our secondary equation here, which variable should we solve for? Probably y, probably x. Actually, it doesn't matter. You just solve whatever side, solve whatever measure you want to here. I'm going to solve for x because that saves me one step of, all I can do in one step, I can just subtract the 2y over. Okay, but if you want to solve it for y, feel free to. And then, see how things match up. That's fine. I don't really, have a problem with that. This one's pretty straightforward, I think. So if you want to solve for y, feel free to. We should end up with the same result. Okay. So then we'll replace the area formula here. We'll replace that with a 3,000 minus 2y times y. Should I go ahead and take the derivative at this point? No, you can, but why make it harder? Let's go ahead and distribute that y first, so we don't have to do the product rule. Okay. Notice in these problems that we're not differentiating with respect to t. No dy dt shows up, no dA dt. We're just taking the derivative with respect to whatever variable happens to be in our problem here. So, back here, where we rewrote our volume in terms of x, we were just taking the derivative with respect to x here. That's all. We're not interested in how this is changing with respect to time. We just want to know how it's changing with respect to x in this case. Okay? We're not interested in that. Same thing here, right? We rewrote things now in terms of y, so I'll take the derivative of this with respect to y. So we end up with, a prime. If you want to call it dA dy, that's fine, but a prime is okay too. Derivative of 3,000y is just 3,000, and then minus 4y. Okay? We've got the derivative. Now what should we do?
Set it equals 0.
Set it equals 0, find those critical
I got
points.
something right.
Good job. Okay. And so we get 750. Okay, if we do that. Of course, we want to make sure that we're labeling things too, so 750 feet. All right, again, we've only come up with one kind of critical number here, so we're really hoping that this is going to be a maximum. Otherwise, we're going to maybe not be able to build this thing. Okay, so let's go ahead and do that. So again, I'm going to start with 0 being like the left end point of that number line because we really can't talk about having, a fenced-in field if y is 0. And then we'll put 750 in there. Okay, and so let's pick a number between 0 and 750. I'll say like 1. All right, we'll plug 1 in here. 3,000 minus 4 is positive. All right, and then we'll pick 1,000. That's to the right of 750. Let's pick 1,000. 4 times 1,000, 4,000. 3,000 minus 4,000, negative. Okay. So is 750 a maximum? Yes. Okay. So we want to find the dimensions, though. We want to find the dimensions. So 750 is one of our dimensions. And then we'll do what Sean suggested we do, and we'll plug it back into that one where we solve for x. So we'll say x equals 3,000 minus 2 times 750. Okay, 2 times 750, 1,500. 3,000 minus 1,500 is 1,500 itself. Okay, and so there are our dimensions. 1,500 feet by, 750 feet. Okay, or you can just say the x and y there. That's fine too. You don't have to circle that additional one. You don't write that additional one there. Okay, questions on that? Yes, Gabe?
So you plug 750 back into
The secondary equation. And the reason why we did that is because that secondary equation has just two variables, the x and the y. Here, the a, x, y, we don't know what the a for any particular value, so we want to use the secondary.
Wait, so in the answer, you circled 150, what's the, oh, that's,
That's supposed to be like an x, like a by, like 3 by 4 or something like that, 3x4 kind of thing. But you can, again, you don't even need to put that, Lily. This is sufficient right here. You've got your two dimensions right there, so that's sufficient too. Okay. Okay, let's continue on here. Okay, so a rectangular page. A rectangular page is to contain 54 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be? so that the least amount of paper is used. Okay, so this is a rectangle, and it's a page, so most likely it's like this kind of rectangle, right? Okay. Very paper-like, yes. Okay. The important part is the shading. That's what makes it look like paper. Okay. The margins, so we got 54 square inches of print. Okay, that's a piece of information we'll probably need there. The margins at the top and bottom of the page are to be 1.5 inches, right? So, like, you guys know what the idea, understand the idea of margins, right? They're like the things that you that you lengthen if you need to make your paper longer, so that way there's more print and then it jumps to the next page and stuff. No. But that we obviously, when you print a paper, right, you don't print to the edge of the paper or to the very top or bottom of the paper. You have these things called margins, right? Okay, so that you only print within like an imaginary rectangle inside the rectangle of the paper, right? It creates an imaginary rectangle inside the rectangle of the paper. So the margins at the top and the bottom of the page are 1.5 inches. So that means from the top, we're going to go in 1.5 inches. And from the bottom, we're going to come up 1.5 inches. Okay? And then from the left and the right, we're going to come in 1 inch. Okay? And all of those margins together create this kind of imaginary printable rectangle here that we normally don't see, but we're going to draw for our purposes. And then here is where the writing would be, right? Okay? Something like that. Wavy lines, right? What should the dimensions of the page be so that the least amount of paper is used here? So we have a little bit of freedom about how we, describe, how we put the dimensions for things and stuff like that. Okay, we could say X and Y here, X being the full side of the sheet of paper, Y being the full side of the sheet of paper, or we could say X and Y being X the full side of just the printable space and Y being the full side of the printable space. Okay, so we have kind of two different ways we can kind of set this up. We can say X is the imaginary rectangles, this way, and the Y is the imaginary rectangle this way, or we could say X is the full sheet of paper this way, and Y is the full sheet of paper this way. I didn't check on this, but I'm pretty sure that we want to go with the simplest primary equation we can here. Okay, so let's go back to ask the question: what is the thing we're trying to maximize or minimize here? Minimize the area of what? The paper, so that would be the whole thing here, right? The whole thing. So let's just call the whole length here X and the whole length there Y. And so then we want to minimize that area, which is equal to XY. Okay, so area still equals XY. But of course, what's our problem here with this primary equation? You got two variables, two independent variables. So we need to come up with a secondary equation. Oops, I don't know why I put an S there. You don't need to put these labels, by the way, primary and secondary. If it helps you, feel free, but I'm just doing it because these are notes, and I want to, help you guys be able to read back to things, okay, and label things. Okay, so secondary equation. We know that the rectangular page is to contain 15 square inches of print. So the key thing here is of print. That is the little imaginary rectangle right there. So our area is going to be 54 for that. Must contain that much. What is the length of this imaginary, or this distance right here? X minus 2. Very good. X is the full distance. We take an inch in from each side. That's a total of 2 inches in. So it'll be X minus 2. And then what will be this length right here? Y minus 3. Again, we're going in 1.5 from each side of Y. That's a total of 3, so it's Y minus 3. Okay. Which variable should we solve for here? Doesn't really matter. I'll solve for X because that's what I heard someone just say right there, so we'll solve for X. So we'll divide both sides by Y minus 3. Okay, divide the y minus 3 over, and then we'll add 2 over. Whoop, not times, plus 2, Mr. Wood. There we go. And now that we have that, we're going to plug into our primary to get that in terms of a single variable. So it will be 54 over y minus 3 plus 2 times y. Okay. Let's not just leave it that way. Let's go ahead and distribute the y. Okay, before we take the derivative here. So we end up with 54y over y minus 3 plus 2y. At this point, it's really up to you with how you prefer to do things. If you like, you could take the derivative at this point. Actually, we could have taken the derivative right here if you prefer. I would say no one maybe would prefer that. But at least from here, you can decide, okay, I'll take the derivative here. It's going to require me to use like a quotient rule. Not too bad and stuff like that. Or you could go ahead and combine like terms by getting a common denominator, right? So that's another option. You can combine this into a single fraction and then take its derivative. Really up to you how you want to proceed here. I'm going to take the derivative as it's currently written, okay, using the quotient rule. Don't forget to take the derivative of 2y there. It's 2, right? There's a plus 2 at the end there. Okay, so we're going to have 54y, but minus 54y, so they actually cancel out. So we'll just have negative 3 on the top over y minus 3 squared.
Negative 3 times 54.
Oh, thank you, yes. So it would be negative, it's 162. Thank you. Sorry, yes, the 54 also distributes to the 3. So the 54y minus 54y, they're gone. But then a negative 3 times 54, negative 162. Yep. Okay. And of course, what do we do now? We've got the derivative, but now what? Set it equal to 0. Okay, so we'll subtract the 2 over. And let's see here, we have y minus 3 quantity squared. Okay, we'll multiply both sides by that y minus 3. Okay, and so that's gone there. We're left with y minus 3 quantity squared times negative 2 equals negative 162. Now, we may be tempted here to kind of FOIL out that y minus 3 and go from there, but actually I think that's going to make things more difficult. If we proceed from here, we'll divide both sides by that negative 2. We'll get 81. And then from this point, what can we do to both sides? We can square root, yeah. So we get, I'm going to run out of space here, but y minus 3 equals plus or minus 9. And so then y equals, or I should say y minus 3 equals 9. Y minus 3 equals negative 9. And so we get 12, and we get negative 6. Okay. Can we throw out any of those critical points? Negative 6. Are these all the critical points? There's one other critical point we missed. We set the derivative equal to 0, but in this particular situation, the derivative could also not exist when y is what? 3. So we also want to check y equals 3 as a critical point as well. Okay, again, so we'll set up our number line there, again, because you have the y minus 3 in the denominator there. I'll set up the number line. I'll put 0 again as our lowest possible value because it wouldn't make sense to make a page that is a height of 0, just y, okay? So we'll put in both of our critical points here. All right, so we'll try again. We're plugging it back into the derivative, so we'll try a y value of 1. So let's see here if I can do this easily. So, well, it's going to be 1 minus 3. That's going to be squared. Okay, so 1 minus 3 will be negative 2 squared will be 4. Negative 162 divided by 4, that's going to be a pretty negative number, and you're going to add 2 to it. It's still going to be negative, right? Okay, let's try a number between 3 and 12 here. So we'll try 10, okay? 10 minus 3 is 7 squared is 49. Negative 162 divided by 49. Ooh, that's going to be a bit closer, isn't it, here? Let's see. Maybe I should have picked something smaller to help. Let me do 4. That actually is an easy number. 4 minus 3 is 1. Squared is just 1. We have negative 162 over 1. So it'll still be negative 162 and then plus 2. So it'll still be negative there. Okay, and then beyond 12, well, now we have a lot of options here. I don't know, we can say like 50 if we wanted to, 100 if we wanted to. Certainly that's going to be then, really big here, squared, even bigger. Negative divided by that really big number is going to be still negative, but a very small negative, adding 2. We're going to get positive there. Okay, we're going to end up with positive there. Okay. So where's our relative minimum? Y equals 12 and 12 inches. Okay, and then are we done? What do we still have to do? Find the x. So the x is, we can use that primary equation or the secondary equation rewritten there. So 54 over 12 minus 3 plus 2 equals x. You can put that in inches and just circle it if you want to. Remember, you don't have to simplify the arithmetic there. Okay, but 54 divided by 9 is 6 plus 2 will be 8. So you could also just say 8 inches instead there if you wanted to. Okay. But there's our answer. Okay, questions on that one at all? Okay. So why don't you guys go ahead then and try number 4, okay? Try number 4, okay? And that's where we're going to stop today, okay? We're just going to do up to 4 there, all right? So try number 4, see what you can come up with there. For that, the product of two positive numbers is 200. Minimize the sum of the first and twice the second. Okay? Minimize the sum of the first and twice the second.
Yeah, no. The answer to the last one was x is 8 inches, or the page width is 8 inches, and the page height is 12, right?
Height is 12, width is 8, correct.
Mr. Woodmark.
Okay, solid. Did you do it with your x and y for the inside parts of the page? I'll come take a look at it in just a second. Okay, so there's number 4. Go ahead and give that a try here. Okay. Nope, that's right.
Minimize the sum of the first.
Minimize the sum. So what do you sum? What do you add?
X and Y.
What does it say? The sum of what?
The first.
So that would be like
Oh, okay,
x.
so X plus 2Y.
That's equals s, your sum.
This is my secondary equation then.
What's the thing you're trying to maximize or minimize?
Sum.
So that is therefore your
Primary.
primary.
So is this my secondary
That's your
equation?
secondary.
Oh, just give it to us in the backwards
So
order.
yeah, exactly. So you would say s equals that. Actually, the typical order is the primary equation does come with the same thing because you're like normally the question normally we ask the question at the end. What is the minimum of this thing? What is the maximum of this thing? Sometimes it's within it, but normally it is at the end actually. Oops.
Do I take the derivative or do I set it equal to 0 first?
How do you normally find a maximum or minimum of a function?
Take the derivative.
Take the derivative first. Okay, go ahead and do that one. Run up.
Oh, no.
The values are 0 and 20.
Sorry, what did you use? So write that somewhere. Now, what's the problem here? You're trying to secondary.
Ten is because I got Y.
I did.
It's part of creative writing. It's like a poetry recitation.
So is that just a way to help that? It's pretty nice.
I was trying to take the word picture.
And that's X to the next one.
Like, I did Y. I did Y. So then Y. So I took the word picture, which is 200 divided by Y, plus 2Y. So then Y times 0 becomes 0. Right. Y, so that's 2 divided by Y plus 2Y. I can go into like, so you get Y times 0, the derivative, well, and the derivative of I, which will get you Y times 0. Minus the top,
Right.
Oh, no way. We still might be right. We're still down to backwards.
I did it, I changed it, and then like, it didn't work, it's like your password's the same as your old password, I tried to change it, it seemed like it was right.
Understand? Yeah. Even it's not gonna be right. Yeah. So it's gotta be 20. But 10 could be right.
It is right, Sarah. It's not. It's not. Yes, you go to. I did. So it is right. Right, Chloe. Right. Shake your head yes. It wasn't gonna be a shake your head yes. I got X equals 20 and Y equals 10.
One sec. Let me just check something here real quick.
Yeah. Not that hard, just takes a little.
What?
I wish we already left.
Let's go with the business. I'm just gonna go lay down on the couch.
Is that all you did?
Yeah. I was like, 4 o'clock, I just went down the couch. He was so mad at me sometimes. Just
Okay. All right, folks. Hopefully you've had a chance. Okay. 20 for the one for the first, I guess we'll say, and 10 for the second. Okay. So 20 for the one and 10 for the second. Okay. Those are your two there. questions on that at all?
How are you?
All right, so this one it's so simple, right? It's like two tiny sentences, and not like the ones we did before, so maybe it made it a little more difficult, right? In that sense. But again, the sum, okay, minimize the sum. That's our primary equation right here. Sum of the first and twice the second, so x plus 2y. Okay, but of course the problem, two different variables. So we use the secondary equation here. Again, it is not necessary to label these things primary and secondary. I'm just doing it for the notes. But we do get that y is 200 over x, which you can plug in here. I rewrote it as x plus 400x to the negative 1, took the derivative, so on and so forth. You get the idea. Ooh, I didn't analyze to make sure that it was a minimum there.
Oh, it is.
It is a minimum?
It has to be.
Okay. It has to be, Mr. Wade. Just take our word for it.
I mean, it looks right, so why even bother?
No, I can see that, it's going to be plus and
Only got
minus.
one answer.
Yeah. Okay. Your homework is posted to Google Classroom. Okay. Emily, set.